Good morning, students. In the last class, we discussed the quantum conditions and the quantization of real scalar fields. Scalar field is nothing but a single entity we discussed in the last class. So this will have a single entity and this will have real values as well as complex values. So real value means a photon which will create a particle. That particle will create an antiparticle. I repeat, the photon will create particle and antiparticle, the same entity. That's called a real value. Suppose if there are more than two particles, number of particles exists, then we have to go for the complex field. Real field means for a particle, that particle will have an antiparticle. Whereas if suppose we are going to go for more than two systems, more than two particles, we will have number of antiparticles, number of particles, then the combination will be complex scalar fields. Okay, that's the difference between real and complex fields. In this class we are going to discuss only the complex scalar fields, in which surely there will be more than two systems, more than two particles, two antiparticles will be there. So in the whatever we discussed for the real field, that will be applicable for the complex field too. So we started with modified Klein-Gordon equation, in which bosons will be applicable, that we know already, in which the field operators will exist. Field operators nothing but phi and pi. Your phi is a field function which depends on position and time. Your pi is momentum density, momentum per unit volume, that also depends on x comma t. So those two entities are called field operators, your phi and pi. So modified Klein-Gordon equation which contains the field operators, and these field operators will be converted into the creation and annihilation operators through Fourier transform. So this is what we discussed, and at the end we are able to obtain the energy of the photon, the quantized energy of the photon. We have quantized the field and thereby we have obtained the quantized energy of the photon. That photon only, as I said earlier, that photon only will create particle and antiparticle. So you have particle, that particle and antiparticle, together what will give us real field. Suppose if there are number of particles, number of antiparticles, then we can't go with which combination will take place, which we cannot judge. At that time we will have to go only with the complex scalar fields. So complex scalar fields in which you have surely more than two particles will exist. So 1 and 2. 1 represents one particle, then 2 represents the another particle. Another particle will have another antiparticle. The first particle will have another antiparticle. Which combination we do not know. The same procedure that we are going to follow. We are going to follow the same procedure as we have done for the real fields, real scalar fields, in which we are going to convert the field operators in terms of creation and annihilation operators, and we are going to obtain the quantized energy of the photon. The quantized energy of the photon for the real field we obtained was E equals h bar omega n plus 1 by 2. Correct? H bar omega n plus 1 by 2. N is a number operator. H bar omega is the energy. And also we discussed about the 0 point energy when n equals 0. That also we discussed. 0 point energy in the vacuum state. Here too we are going to obtain the same expression for the quantized energy of the photon. So h bar omega n plus and n minus plus 1. I repeat, h bar omega n plus n minus plus 1. N plus half we know already. N plus half we know already. Here we are talking about one positive energy, then another one is negative energy. As I said, two particles. Correct? One positive energy, then another one is negative energy. So n plus half, n minus plus half. Half will give you 1. So n plus n minus plus 1. Very simple. So at the end we are going to discuss. So with this introduction, we will start the quantization of complex scalar fields. If the field functions phi of a scalar field are complex, then we have a complex scalar field which describes a charged particle in the quantized theory, in quantum field theory. The quantization of complex field is derived similar to the real scalar field. If we know thorough with the real scalar field, it will be very easier for the complex scalar fields. It was first carried out by Dirac-Pauli and Weishoff. We know that the complex field is described the field variables. We know already field variable phi, which depends on x comma t. For the time being, we can pull t equals 0 for the simplicity. So phi depends only on x by splitting into real and imaginary parts. So phi is nothing but phi 1 plus I phi 2 divided by root 2. So this is for the first particle and this is for the second particle. Okay. So phi 1 plus I phi 2 divided by root 2 is a complex number. Both are phi 1 and phi 2 are real numbers. This is complex part, I phi 2. Phi 1 plus I phi 2. Complex conjugate of this will give you this. But as I said just now, field function, field operators as I said just now. So in quantum field theory, we are talking about only the wave amplitude. Phi is nothing but a field function, field operator. So we should not take the complex conjugate, we will have to take the dagger. Okay, for any operator, we will have to only take the dagger. So your phi will be this one, your phi dagger will be this one. Okay, so in next class, next slide we are going to find out, see. So we are going to go only with the phi dagger. Now phi and phi dagger are here and they are not the same. You have taken the part and you have taken the complex conjugate of and with dagger, Hermitian conjugate, and they are not the same. So we can conclude that phi is not equal to phi dagger. So they are not Hermitian. If it is so Hermitian, then phi equals phi dagger. Okay. The real fields phi 1 and phi 2 can be expressed in terms of their creation and annihilation operators, as we discussed for the real field. Already we know that. So phi 1 is connected with this. So phi 1 is a field operator for the first particle. Okay. So which is connected with the creation and annihilation operator. So this is your destruction operator. This is your creation operator. Annihilation operator and creation operator. This expression already we have used in the real fields. Already we used. So this is for phi 2. This is for phi 1. 1 by root p sigma over k root of h bar divided by 2 omega k ak1 e power ikx plus ak1 dagger e power minus ikx. So phi 1 and phi 2. Now use this relation. So phi 1 plus I phi 2. So phi 1 plus I phi 2 will give you, you have to multiply with I and you are going to add these two, divide by 2, that will give you phi. Taking the complex conjugate, that will give you phi dagger. Is it okay? Simple idea. So you are going to add these two. When you are going to add these two, real with real, imaginary with imaginary, you have to add already. So we know already. So ak1 plus ak2, take the common out, that will give you e power ikx. See here, e power ikx, we have taken the common out. This is ak1 plus I ak2. Phi 1 plus I phi 2. I phi 2. So that's why I have written as ik2 divided by root 2. Similarly, for the next one, that will give you ak1 plus I ak2 dagger divided by root 2. See here, ak1 dagger plus I ak2 dagger. Just take the common out, that will give you e power minus ikx. Any doubt in equation 10.91? Just take the complex conjugate. Just take the dagger, Hermitian conjugate, that will give you this expression. So wherever you can find I, you just substitute minus I. So you will have ak1 minus ik2. Okay, ik2. So e power ikx becomes e power minus ikx. Similarly here plus I, that becomes minus I. So e power minus ikx becomes e power plus ikx. Is it okay? Expressions for phi of x and phi dagger of x. Is it okay? Now we are going to simplify these terms. We are going to simplify these terms using this expression. ak plus or minus, which is equal to ak1 plus or minus iak2 divided by root 2. Now wherever you find plus, you can substitute ak plus. Wherever you find minus, you can substitute ak minus. So now you have found out, see here, ak1 plus iak2 divided by root 2. So this can be replaced with ak plus. And what of this one? This one, ak plus minus ik2 to dagger. So you have to go only with dagger. For the timing, leave it. This can be replaced with ak plus. This can be replaced with ak minus. Very simple. So this is replaced by ak minus. Now coming to these two terms, you have, this is dagger is there. This is real part. This is imaginary part. When you take the Hermitian conjugate of the real part, that term itself. Correct? ak1 dagger equals ak1 itself, because this is the real part. This is imaginary part. So you have to take, this will go with minus iak, correct, ak2 dagger. This will become, I repeat, see, this is a real part, this is your imaginary part. You are going to take the complex conjugate. Okay, so this is a real part. So ak1 dagger equals ak1 itself. This will become minus. So this term will be replaced by ak minus dagger. So we have ak plus or minus dagger equals this one. So you have ak minus dagger, that will give you this term. So this will be replaced with ak minus. Is it okay? What of this term? This term will become plus. So ak1 dagger plus ik2 dagger. So this will become ak plus dagger. Have you understood this? Okay, I repeat. See, this term is replaced with a plus. This term is replaced with a minus. Simple idea. Now this is your real part. This is your imaginary part. For any real part, if you are going to take the Hermitian conjugate, the term itself you will get. You will get it, the term itself. So ak1 dagger will become ak1 itself. Okay. Now you are going to take, this is your complex part. You are going to take the complex conjugate. So this will become minus iak2 dagger. So similarly this will become plus. If it is minus, and this term will become ak minus. If it is plus, this term will become ak plus dagger. So this term phi of x, this term becomes a plus, first term ak plus e power ikx plus ak, as I said, this will become minus. So ak minus dagger e power minus ik dot x. This will become, what is this one? So ak minus, what is this one? ak, see, ak plus dagger. Now as usual we will have to use commutation rules, as we have done for the real scalar fields. So these are the commutation results that we are going to use. The self ak1 akj dagger, the self one will be 0, whereas ak1 akj dagger will be equal to ih cross del kk dash del jj dash del ij equals 1 comma 2. So these are the commutation rules for creation annihilation operators, and these are the rules for field operators, commutation rules for field operators. We have used the same commutation relations in real scalar fields. So we are going to use the same commutation relations here too. So phi of x comma phi dagger of x with the commutation relation, that will be ih cross del x minus x prime. Similarly phi of x phi dagger of x prime, that will give you ih cross del cube x minus x prime, because del cube stands for your, because 3 dimension, because we are talking about only the momentum density, momentum values per volume. So that's why we have used del cube here. Any doubt? As I said, self one will be 0, self 1 aki akj, that self one will be 0, the dagger will be equal to ih cross. Okay. Now the operators ak plus, this is your annihilation operator, this is your creation operator. So AK plus and AK plus dagger is interpreted as destruction and creation operator for positively charged field, and this is for the negatively charged field. Okay, so this is for the particle and this is for the antiparticles. So negatively charged particle stands for the particle, and this one will give you antiparticle nature. Okay, the annihilation and creation of momentum densities corresponding to real fields phi1 and phi2 are respectively, we know this one. Similarly, we can go for the momentum field operator, momentum density field operator, which is nothing but pi of x is given by this expression and pi dagger of x is given by this expression. We should know pi and pi. Okay, we should know pi and pi. Pi stands for momentum density operator, pi stands for field operator. Any doubt? Okay, so this is your Klein-Gordon, modified Klein-Gordon equation, this equation which contains pi and pi field operators. And as I said earlier that this will be applicable only for the bosons. We are going to get the expression for the quantized energy of the photon. Photon is a boson. Is it okay? Ultimately, we are going to get the expression for energy of a photon. We will have to use only Klein-Gordon equation, not the Dirac equation. So there are two equations that we know for the relativistic quantum mechanics. One is Dirac equation, which is applicable for the fermions. Klein-Gordon equation applicable for the bosons. Here we are going to discuss only for the photon. Photon is a boson. So that's why we have used Klein-Gordon equation. Okay, spin zero particle. So the total Hamiltonian for the field is given by this expression. We know already. So this is modified Klein-Gordon equation in terms of field operators phi and pi. We know already this. So pi squared is nothing but pi dagger pi. Your phi squared is nothing but pi dagger pi. Del phi squared is nothing but del phi dagger del phi. We know already the expression for phi and pi dagger, pi and pi dagger. Just now we know the in terms of creation and annihilation operators. Just to differentiate with respect to x will give you del phi. So we can take del phi dagger easily. Okay. So now we are going to substitute the expressions for phi squared, and del phi whole squared. Okay. This in this expression 10.99. So using equation 10.93, 10.94, this is for your phi and this is for your pi for the first term of equation 10.99. So this term. So we are going to first take this term, and use the expression for your pi and pi dagger. So integration over d cube x will give you, this is your pi dagger and this is your pi. See here, this is your pi dagger, this is your pi. You have I terms here. Here also just take the Hermitian conjugate, that will give you minus I. See? Is it okay? So this is your pi dagger, this is your pi. Now you have I here, I multiplied by I squared minus 1, already one minus is there, so this will become plus. First point. Second point will be 1 by root p multiplied by 1 by root p, that will give you 1 by v. Then third one will be h bar omega by 2, h bar omega by 2, that will give you under root. So h bar by 2. It comes under root. Here it is omega k, but here it is omega k prime, because we have taken the complex conjugate. So k will become k prime. So omega k prime. So that will be root of omega k prime. You will have to multiply these two terms. Okay. So multiplying these two terms will be, you are going to multiply first term with this one, first term with second term. Then second term with the first term, second term with the second term. So that's all. So equation becomes, as I said, 1 by root p, h bar by 2, root of omega k prime, integration over d cube x, first term with the first term. See here, first term with this first term. So ak minus dagger with ak prime plus dagger. See, ak minus dagger with ak prime plus dagger, and the phase factor will be e power ikx multiplied by e power minus ik prime x. See, I have written as e power I k minus k prime x. Any doubt in the first term? Similarly, you can go for the first term with the second term. So you have ak minus dagger with ak prime minus. See here, these two terms. You have e power ikx multiplied by e power ikx prime. See here, I have taken as common out x. So e power I k plus k prime x. Similarly, you can go for the third term and fourth term. Any doubt? Now, this will come under summation. This term will come under summation because sigma over k and k prime. Whereas this term d cube x, so this is in terms of integration. Now 1 by v, when you are going to integrate, these two terms will get cancelled. This will become 1. 1 by v integration d cube x, that will become 1. So you are going to have only summation alone. Is it okay? Summation. So sigma over k prime, this term will be there, and we are going to use canonical delta function as we just now we did. E power I k minus k prime. First we will go for k and k prime. If k equals k prime, that will give you del k prime. If k equals minus k prime, that will give you del k minus k prime. Similarly, this will become k plus k prime. So this will become del k prime. This will be your k equals k minus k prime. So this will become del k minus k prime. Any doubt? Now, if k equals k prime, this will become 1. Okay, according to canonical delta rule. So this will become 1. So k prime becomes k. Similarly, here also k equals k prime. This k prime becomes k. This will become 1. Though, see here. First, these two terms are there. Now, what of this term? When k becomes minus k prime, this will become 1. I repeat, here it is k equals k prime, but here k prime equals minus k, or otherwise k equals minus k prime, or otherwise minus k prime equals k. Everything is the same. So if you have minus k prime equals k, this becomes 1. I can say that k prime equals minus k. So k prime is replaced with minus k. See, this term, let it be like this. You have this term alone is changed as minus k. Any doubt? Similarly, here too you have k prime equals minus k. So this will become 1. So k prime is replaced with minus k. See, minus k. Any doubt? You are going to use continuously this technique only, okay, throughout. So if you have doubt, then we can't continue. Any doubt is there? So we have found out the first term in Klein-Gordon equation. So we have found out the first term.